So, welcome everyone again to the Introduction to Game Engine Programming by Connor Walsh. So, the goal of this workshop is for you to learn about the programming behind game engines so that you can understand that it's not just some magical program that you drag and drop shapes into and tell it what to do. I feel the best way to do this is to actually explain all the aspects rather than to just code something with like no explanation as I go through it. Because the Unity workshop that I did, there was quite a bit of drop off. I feel like people got bored as we just started coding along. I feel like it's better for you to walk out of here with some knowledge rather than to just have copied code. So I feel like that's what I'm going to try to do today. So what is a game engine? Simply put, a set of tools to create a video game, as if that wasn't obvious enough. But most people know that. So today we're going to take a deeper look at what goes on under the hood. And a lot of people tend to think that a game engine is a game engine editor, like what they're used to seeing when using Unity or Unreal engines. However, the editor is just a piece of those engines that allows for even easier usage. So before we start, creating an entire game engine is a massive undertaking that mostly no one will ever fully do on their own. Typically, this would require a large team and a long time, and I didn't put this in the slides, but quite a lot of funds, a lot of money. The workshop is titled Introduction to Game Engine Programming, not Build Your Own Game Engine for this reason. That reason is, while you won't be building an engine from scratch, I do think having an understanding of game engine fundamentals is a great way to learn more about programming. Okay, so there are four main aspects of a game engine. We have the game logic, the graphics, the audio, and the physics. Notice how I say main aspects, because there are tons of aspects, In fact, there are AI aspects now. There are anything you want in a game, you can add into it. But the four core things are game logic, graphics, audio, and physics. So let's get into game logic. Since it seems that most of our IEEE members are computer science majors, this one should be fairly straightforward. The game logic portion of an engine behaves just like any standard program you've written behaves. So even like your intro to Java classes, like it's going to be the same way. You're going to be making objects and they're going to be interacting with each other. So you say you make one object that has a health bar, like a health value, an integer, and then another one that would have a function to lower that said health value. Like it's just basic like C++, Java object-oriented programming. Moving into graphics, modern game engines use very low-level APIs for rendering graphics. These APIs are capable of rendering both 2D and 3D graphics. And the most popular of these are OpenGL, which was mostly famous for being what Minecraft was made in. DirectX, which was made by Microsoft and used by nearly every single AAA developer for making games. And Vulkan, which is relatively new, and some AAA developers have tried integrating it into their engines so that typically in modern games, you'll have the option of using, say, DirectX 12 or Vulkan. So the only one that I really have experience with is OpenGL. I've tried out DirectX, but the thing is, if I had to make a tier list, in terms of which ones are like user-friendly, OpenGL isn't even close to user-friendly at all, and it's still the easiest one out of the three. So we're going to be using that one.
Connor, before you go on, you want to tell everyone what a AAA developer is in case they don't know?
Okay, yeah, I feel like that might be a little bit niche, so I will explain. A AAA developer is like your typical, high budget, extreme production value developer. Let's say, I don't know, Activision, something like that. The ones that churn out all these unfinished, like expensive games that you see advertisements for on like TV. Yeah. Your Call of Duties and your all those kinds of games. Any company that has a lot of money that makes games, basically.
Thank you.
You're welcome. Don't worry about it. So there are lots and lots of triangles that go into 3D graphics. So James actually mentioned this to me last night, but it turns out OpenGL used to know what a rectangle was, but no longer does in 4.0. This is because the way that they had their rectangle shapes implemented, it did not matter because OpenGL broke it down into triangles anyway. So as you can see down here, if you need to make a rectangle in OpenGL, you would simply put two triangles together like such. This is extremely incredible, I know. Having to manage all of these triangles and their positions can be quite annoying. Luckily, OpenGL has a way to manage this. This is called a vertex buffer object. So I have a bit of an example on this. So I wrote here, the simplest way I can describe this is OpenGL will keep one copy of the shape, i.e. a cube, inside your graphics card's memory. And then whenever you want to draw this exact shape, instead of having to resend the function to draw the shape, like instead of having to pass it the vertices again, you can just call to the memory location of the object in OpenGL, and it will remember what you want, and it will draw it. So after this stage, you're just simply shading and determining what the final color will be. So basically, this graph here, or this picture, is really a really good way to understand it. So basically, if you want to draw a triangle, right, you would have 3 vertices, 3 points where of the shape of it. So, you could have, they could be in any sort of positions that you want, any shape of triangle, but what's important is that you have the 3 points. And then, so the vertex shader is what's stored in the GPU, and then you would pass to the shape assembly. It would put it together into a triangle. The geometry shader would determine exactly how many pieces to, it would cut it up into more triangles to, I guess, I don't know, something with the GPU. Honestly, I'm not too sure about that, but at this point, there's the rasterization that actually draws it into a shape that you can actually see on the screen. And then you have something called a fragment shader, which will color it. We're not going to go too deep into the color shadings, but it's just important that you understand that basically everything that you see is made up of triangles. Every 3D model is just tons and tons of triangles, and the more we go on, the more modern things get, it's just more polygons. Okay. I hope I've bored you sufficiently on the topic of 3D graphics. So let's move on.
Do you want to do a question session before we move on?
Sure thing. Does anybody have any questions?
Yeah, I have some.
I would hope people have questions because it's very difficult.
I have a question quick.
Yeah, sure.
So you're saying OpenGL pretty much stores the the object, like the triangle object in the your GPU. How memory intensive is that? Do you how? I guess considering does it depend on how many I guess triangle objects you have, or
Yeah, it's basically like that. I'm still in Chrome, so I can, if I look up vertex buffer object, and then maybe memory, I can show you. I've seen there's a dialog, not a dialog, images, not shopping. So it would be something like this right here. So in the vertex buffer object, there's positions, right? So you'd store one shape at one position and then one shape at another position. So you'd basically just be calling, you would have as many shapes as you need in the memory. And then in the code, you would just call, I need whatever shape is at position 1, and it would grab it and then store it in the pointer, and then it would draw it.
Here's the other thing. I have a comment to make about that. So it's a bit more fancy than what we're letting on here. If we actually take a look at the VBO and the VAO constructors, you'll see that you actually have more to every single vertex than just the position in space. You're also storing texture coordinates, normals, and a lot. You can store as much data as you want in a vertex.
Per object, yeah.
You specify that inside of with the constructor. You can have a single vertex take up as much space as you want. If you just wanted to do like a wireframe, you would literally only need to specify the 3D coordinates using doubles, most likely. I don't know if anyone. So that would be like 64 bits, which is however many bytes that is. I can't divide 64 by 8 off the top of my head. I know it's 8, but you would use basically 8 bytes then to store that. But I mean, this can get extremely memory intensive. Like if you think about any game that has a loading screen, the majority of loading time is sending those vertex buffer objects and textures to the GPU to be stored on GPU memory, so they can be called in real time when the game is being played. Like, think about, I don't know if anyone's played modded Minecraft, but, the load time is horrendous because they have to load in, 7,000, gazillion block textures onto the GPU. So it's it's certainly a very time-consuming process. But once it's on the GPU, it can be accessed like snap. Like it doesn't have to load because it's already there. So that's the core innovation with the whole CPU GPU dichotomy.
Yeah, it's just an interesting thing to note because, you know, I guess it's just not all magic, as you said before.
Yeah, everything has to be done extremely manually when it comes to OpenGL and just 3D graphics in general.
Connor, do you know if DirectX is supported by platforms other than Windows? I know DirectX is really like
it's
Windows
supported on. I know it's supported on Xbox because it's made by Microsoft, and that's how they allow the ports to be made so easily.
Okay.
But I want to say I'm like 95% positive it does not work on any other OSs. That's actually why I think Vulkan is being introduced, because I believe it works on Linux as well now. So any game that supports Vulkan can run on Linux.
Yeah, and OpenGL is the true cross-platform choice.
Yes. Which is why Minecraft was made on it.
Of course, of course.
Okay, any other questions? Please feel free. Okay, I guess I'll move on now. So, an audio manager is essential because in a game, there will be multiple objects emitting noise at varied distances from the players, and also music. It is important to handle this in such a way that the audio is mixed properly and does not destroy the end user's eardrums. After all, bad audio is the fastest way to ensure an Alt F4. A typical, simple solution for this is to have a singleton class as a dedicated audio manager that would be able to be passed the name of a certain audio track to then be played. So a typical way to do this would be to implement like a queue into the singleton to have audio be played at certain times, but also you'd want certain audio functions to be able to mix them properly so they could be playing at the same time and at varied distances. So I guess I should ask, because I know that most of our members are freshmen and sophomore. Does everyone here know what a singleton class is? If not, I can definitely explain it.
Explain it.
Okay, cool. Just needed that little go ahead. So a singleton class is when you have it's very tied to the name. A singleton class is when you have one instantiation of a class that you use throughout the entire code. So the best way I can explain this would be, say you would have an audio singleton, you would instantiate like an audio manager, right? And you wouldn't have audio manager 1, 2, 3, and 4. You would just have a single one of them to handle all of your audio. That would be, I think, in layman's terms, what a singleton is.
Makes sense.
Cool. Okay. Everyone good on that?
Why use a singleton over a static class?
Well, you can actually use a static class is definitely a good option for it too, because then it would follow you through different levels and such, like when you were to move to a separate area or have to like load different code. Typically, you can make. Am I correct in saying that you could have a static singleton if it's only instantiated once throughout the entire code, or not?
I'm pretty sure a static is basically a singleton by default.
Yeah, right.
But I don't know if you would refer to it as a I don't know if you would ever refer to a static class as a singleton, because it's kind of like implied by default that by being static, you don't get to create instances, and therefore there's only one, right?
Yeah,
so
true.
That's
I know that for when I used Unity in I don't know if I did it in the previous workshop, but I definitely did it over the summer, that we had a static singleton class for our audio manager.
Okay, that's interesting.
Yeah. Any other questions on audio? I have a video which I will put in the workshop text after the presentation on audio. We are not going to watch it now because I believe it's about an hour and a half. But if you are interested in audio, or just, I believe it does not have everything to do with just game programming. This is basically the standard audio in C++. So it's very interesting to see how, like, at the extremely low level, how audio is processed in code. So I recommend everyone takes a peek at it, at least skims through it, but you can watch that on your own time because it's quite long. So physics are the fun part. Typically, every single game object will have its own properties, such as mass, collider shape, velocity, etc. This makes things a bit simpler when determining how objects should react to and with other objects. A physics engine will typically have functions to handle the input locations, velocities, and output locations. The input locations and velocities, and the output locations and velocities. At a super high level, it's nothing more than calculus, just a lot of it. So this is a video that we are going to watch. I believe it's about 6 minutes. So I'm going to click it. Okay, can everyone hear this? I just want to triple check.
You gotta play it.
Physics engines are responsible for figuring out where each object
Yes.
scene is over
Yeah.
time.
Yes,
Okay.
playing.
Collide with one another, then choose to respond in several ways. It's a generic problem that the user can configure at several different levels. Do they want a collider? Do they
Is a
want
little
to-
low for everyone else.
Do they want to simulate dynamics?
You can
It's
turn
about
up
dynamics,
the.
but not
Did you
gravity.
turn it up
It's a
already?
problem
It's
that calls
pretty
for
loud
good
for me.
planning and robust design.
Oh, yeah, that's my
The problem
fault.
can be split into 2 or 3 pieces: dynamics, collision detection, and collision response. I'll start with dynamics because it's by far the simplest. Dynamics is all about calculating where the new positions of objects are based on their velocity and acceleration. In high school, you'll learn about the 4 kinematic equations along with Newton's 3 laws, which describe the motion of objects. We'll only be using the first and third kinematic equations. The others are more useful for analysis of situations, not simulation. That leaves us with these 2 equations. We can give ourselves more control by using Newton's second law, subbing out acceleration, leaving us with this formula for the velocity. We'll use this struct to store the object info for now. We need a way to keep track of the objects we want to update.
Is everyone familiar with structs in like C and C++? If you are not and you've only used Java, think of struct like an extremely stripped down and basic version of a class. That should get you enough knowledge for this video.
A classic approach is to have a physics world with a list of objects, and a step function that loops over each one. Note the use of pointers. This forces other systems to take care of the actual storing of objects, leaving the physics engine to worry about physics, not memory allocation. With this, you can simulate all sorts of stuff, from objects flying through the sky to solar systems. You can do a lot with this, but it's the easy part, to be honest, and that's not what you came for. Collision detection is more involved, but we can lighten the load by using some clever tricks. Let's think about what needs to be found first. If we look at some examples of objects colliding, we notice that in most cases there is a point on each shape that is furthest inside the other. This turns out to be all we need to respond to a collision. From those 2 points we can find the normal and how deep the objects are inside one another. This is huge because it means that we can abstract the idea of different shapes away and only worry about the points in their response. Let's jump into the code. We'll need some helper structs to store the points of the collision and the location of both objects. Each shape will have a different type of collider to hold its properties and a base to allow them to be stored. Any type of collider should be able to test for a collision with any other type, so we'll add functions in the base for each one. These functions will take transforms so the colliders can use relative coordinates. I'll only demonstrate spheres and planes, but the code is repeatable for any number of shapes. Let's make both types of colliders at the same time so we can see how they interact. A sphere is defined as a point and a radius, and a plane is defined as a vector and a distance. We'll override the functions from collider, but won't worry about the work for now. In cases like this, where there are many classes with a web of similar functions, it can be confusing as to where the actual code is located. Sphere versus sphere would obviously be in the sphere.cpp file, but sphere v plane could either be in sphere.cpp or plane.cpp. There's no way to know without hunting, which gets annoying when there are many files. To get around this, let's make an algo namespace and put the actual work in there. We'll need a function for each pair of colliders we want to be able to check. I've made a sphere v sphere, sphere v plane, but not plane v plane because it's not so useful. I'm not going to cover these functions here because they're not part of the design per se, but you can check out the source if you're interested. We can choose per collider which other colliders it will detect by filling or not filling in these functions. In this case, we don't want plane v plane collisions, so we return an empty collision points. We can add a function for testing the base and use a technique called double dispatch. This takes advantage of the type system to determine both types of colliders for us by swapping the arguments, determining the first, then the second type through 2 calls of test collision. This saves us from needing to know what type of colliders we are checking, which means we've fully abstracted away the notion of different shapes outside the collision detection. You can use these colliders on their own, but most likely want to attach one to an object. We are still only using position in the dynamics, but can use scale and rotation in the collision detection. A good design practice is to separate all the different aspects of complex functions like step into their own. This makes the code much more readable, so let's add another function named resolve collisions in the physics world. First we'll need another helper struct to store the points and the objects involved. This is looking good. Because of that double dispatch, there's no need for anything other than a single call to test collisions. Using a break in the for loop gives us the unique pairs, so we never check the same objects twice. Now that we have detected a collision, we need some way to react to it. Because we have abstracted away the idea of different shapes into points, the collision response is almost pure math. The design is relatively simple compared to what we just went through. We'll start with the idea of a solver. The solver is used to solve things about the physics world. That could be impulse from a collision or raw position correction. Really anything you choose to implement. We'll need another list in the physics world to store these, and a function to add and remove them. After we generate our list of collisions, we can feed it to each solver. In the last section, the meat was in the design. This one leans much more towards what kind of solvers you implement. I've made an impulse and position solver myself that seem to work for most situations. To keep this short, I won't cover the math here, but you can check out the source for the impulse solver and the position solver in the description if you're interested. Let's see a demo. The real power of a physics engine comes from the options that you give to the user. In this example, there aren't too many that can be changed, but we can start to think about the different options we want to add. In most games, you want a mix of objects, some that simulate dynamics and others that are static obstacles. There's also a need for triggers, objects that don't go through the collision response, but fire off events for exterior systems to react to, like an end-of-level flag. Let's go through some minor edits we can make to allow these settings to be easily configured. The biggest change we can make is to distinguish between objects that simulate dynamics and ones that don't. Because of how many more settings a dynamic object needs, let's separate those out from what is necessary for collision detection. We can split object into collision object and rigid body structs. We'll make rigid body inherit from collision objects to reuse the collider properties and allow us to store both types easily. We are left with these two structs. A dynamic cast could be used to figure out if a collision object is really a rigid body, but we'll make the code slightly longer, so I like to add a Boolean flag even though it's not considered best practice. We can also add a flag for the object to act as a trigger and a function for a callback. While we're at it, let's beef up the security by protecting the raw values through getters and setters. We can add many more settings to the rigid body. It's useful if each object has its own gravity, friction, and bounciness. This opens the door to all sorts of physics-based effects. In a game you could have an ability that changes the gravity in an area for a time. You could have some objects be bouncy and others like weight balls. A floor could be made out of ice and be slippy for a harder challenge. Let's split the physics world into a collision world and dynamics world as well. We can move the step function into the dynamics world and resolve collisions into the collision world. This saves someone who doesn't want dynamics from sifting through functions that are useless to them. We can make some edits to the resolve collision functions to give triggers their correct functionality. Let's split the function into its parts to keep it readable. Adding a callback to the world can be useful too if you want program-wide events. To keep the step function readable, let's split it up into pieces as well. Now we have a whole stack of options that the user can configure for many different scenarios with a simple yet powerful API. I hope you can use the principles from this video to get a better idea of how to lay out complex systems in nimble ways, or even make your own engine. There's a lot more to cover, but I'll leave that to a part 2 because this is getting long. Let me know what you think.
Okay, everyone. Well, if you didn't know the code, I don't expect you to have just understood everything he just did, but I hope that the video, the demos at least, explain to you the properties of physics engines and how there are certain things that are dynamic, static, certain things that are triggers, and things that should and should not have reactions based on collision. So does anyone have any questions about that video? Not super specifically about the code? If there are no questions, I will move on. Okay, so basically, I just put this little graph in right here to show you that you'll need to calculate new positions and then detect collision and have the result of this collision be sent back to the engine and the entities. Okay, so the next thing is user input. And after all, it can't be considered a game unless there is a player controlling it. We need code that will handle user input consistently and tell the rest of the components of the game engine what to do. But how do we accomplish this? Now, there's something called a game loop in game engines. A game loop is what differentiates a game from a still image. Video games are very resource intensive and unoptimized for our hardware. This is because in order to be ready for user input and change on the screen, we need to constantly loop over everything that we are doing in the engine. Let's say we have a game that runs at 60 frames per second. Then we would need to read the user's input, calculate the physics, re-render the entire scene, determine what audio should be playing, and evaluate game logic 60 times every second non-stop until the user quits the game. So this is a very basic way to look at a game loop. So I guess the easier way to start would be on the right side here. So when you would start up a game, you'd want to process the input, update the game, which would include rendering and physics and all that. Or no, rendering would be down here, but physics would be here and the audio would be here. And then render the frame, and then check to see if the user wants the game to end. And if not, do it all again, non-stop until the user does want the game to end. And it's pretty much the same thing over here. If you start the game, check for input, update the game, render it, wait. What they have here is a locked frame rate at 60, but typically this is not the best way to do it, because then if you get less or more frames than 60, the physics will be very janky. You can see Skyrim as a very good example of this, if you know that. And then it basically will just keep going nonstop until the user decides to stop the game. Okay, so there are two more videos I want to watch and one to recommend, so we will click this one.
Game Engine.
This video is very high level, so you won't have to worry about coding or anything, so should be good to just start playing it.
Engines. If you follow games, you've probably heard about game engines all the time, especially in game trailers trying to hype up their tech, or with all the beautiful Unreal Engine 4 graphics floating around the internet lately. But seriously, can we just take a moment and look at how beautiful these are? Just wow. We hear a lot about advanced engines creating hyper-realistic AAA games, but what do they really do? Does a better engine make a better game? And how could we make one? Let's find out. A game engine is a framework for game development. This framework helps us with several core areas that all games have. For now, we'll simplify it to just 3: graphics, audio, and logic. Actually, these are things that all software has, whether you're making the latest AAA shooter, Tetris, or a calculator app. However, modern game engines have become more specialized and commonly include frameworks for physics, AI, networking, optimization, and much more. But what do I mean by a framework and how does it help? Let's take a look at history. Back in the day, nearly every game was made from scratch. For example, let's say we're making Super Mario Bros. For the NES, and we just got the design sheet from Miyamoto, and we're trying to load the graphics in the right places. Looking here, we have the floor, some pipes, some Goombas, the blocks, coins. We have a lot of objects in this first level. And we have to tell the NES to get these sprites from the cartridge memory and show them at the coordinates that we want them to be at. And once we're finished with this, we then have to delete each and every one of these objects to make room in memory for the next area. So we have to make sure every time we create a new object, we also find and delete every Goomba, coin, and block one by one. Now, this would be a lot easier if we had a system that could keep track of these objects and automatically free them once the next level starts to load. Creating this system will require more memory, but it will also save a lot of development time, which is a trade-off we might want to take. You might notice that every game has objects and characters and enemies, right? So it would be great if this memory management system could be made so it can function in any game, not just one. So that whether you're making Mario, Mega Man, or Zelda, you don't have to keep writing the same code every single time. And this is what I mean by a game engine being a framework. It provides tools and structure that every game requires to function. Using engines means you don't have to reinvent the wheel every time you start a new project. While modern games are able to handle the overhead of many complex systems, in reality, most old school games were not able to take that trade-off, since memory was so limited and precious. Third-party engines only became widespread once 3D games were in demand, and as technologies grew increasingly complicated. Many studios began to use these engines to speed up the development process, although many still make their own in-house engines from scratch, even today. Once again, there is a trade-off here. Making your own engine allows you to optimize specifically for your game, but buying one will save you possibly thousands of hours of coding time. So let's take a look at some of these engines to see what they actually do, how they're different, and how they influence games. First up is GameMaker, which is so simple that I actually used it to make Pong at a science camp when I was about 12. People have made some wonderful and interesting projects with this because you don't have to write code, although you will naturally understand a programmer's mindset as you learn game logic. For example, to make a simple platformer in GameMaker, you need to understand that when the player presses spacebar, the block should jump, but you don't need to understand why things jump in a parabola or how the block is being animated. There are some clear limitations since you have to play by GameMaker's rigid rules, but projects like To the Moon show that creativity and talent can always shine through the tech. Next is Unreal Engine 4, an incredibly robust professional-level tool that recently became completely free to use. UE3 had hits like Arkham City and BioShock Infinite, and Unreal 4 shows a lot of promise as well. You will notice that it looks quite a bit more complicated than GameMaker, and you can see why developers need more advanced software like this to keep track of complex 3D environments. Lots of modern engines will support the cool lighting effects and realistic explosions and other boring things like memory management, but there are two things I really like about Unreal specifically. First, the blueprint system. Learning to make games with this will make a professional engine seem almost like GameMaker. You can get some pretty cool games running quickly without ever writing code. The other thing I like about it is that if you really want to optimize down to the last byte and have complete control over the code, subscribers can have access to all of Unreal's source code to modify it to their heart's content. I love its accessibility to both AAA studios and game dev hobbyists alike. Finally, we have Unity, which has become very well known for being the source of many Steam Greenlight flops, along with some really wonderful titles like Pillars of Eternity, Ori and the Blind Forest, and Kerbal Space Program. Nonetheless, there is a lot of talk about its more unsavory titles. I personally believe that a lot of Unity shovelware exists simply because it has always been free and simple. It supports higher level languages like C# and JavaScript and has many tools that allows developers to bypass coding altogether. Unity has also accumulated a bustling community with tons of free tutorials, assets, and content, making it many young creators' first engine. I personally started with Unity before Unreal, so I'm more fluent in it, meaning I'm able to sketch out game ideas way more quickly, and I'm able to create a lot of content in a short time. Similarly, all of these low barriers to entry result in a huge number of gaming projects in the world at large, of which only a certain percentage will be legitimately good. This is probability's fault, not Unity's. In any case, all of these are wonderful tools that help you make games. Everything I mentioned here has an excellent free version that you can download right now. So if you've always wanted to try making games, you can pull up a tutorial and start making one in only a few hours. So now we have a basic idea of what engines do and how they might affect games differently, but could we make one? Of course we can! So look out for tutorials on how to make a game engine from scratch in C++ in the upcoming weeks. As always, everyone is welcome to try, regardless.
Okay. So I hope people learned, something from that. And I also wanted to show one more video. This is from Linus Tech Tips. Hopefully you know him.
If you're at all
Okay.
like me, you wear the most sensible footwear on earth, you occasionally get excited about the release of a big-name game title, you have at some point in the past heard a friend complain about aforementioned big-name game using the same worn-out old engine, or conversely have encountered the massive hype train that usually accompanies a shiny new engine. But these overly enthusiastic game journalists and downer-type friends often neglect to explain what exactly a game engine is. So, here we go. Firstly, they provide a rendering engine, which allows designers to pair their in-house made 2D images with 3D wireframes to create fully actualized models. Then, usually one or several application programming interfaces, such as the upcoming DirectX 12 and Vulkan, are used to furnish the rendering engine with efficient access to a system's processing and graphics hardware. Secondly, game engines must provide everything else as well. There's the obvious stuff like physics or collision detection engines, which account for general movement and the interaction between models, like, characters and the ground, as well as stuff that you might not have considered before, like realistic lighting effects with realistically bouncing light rays, realistic diffusion through different materials, and even crazy stuff like the scattering of light beneath the surface of a model's skin to give him natural-looking rosy cheeks, for example. And of course, something, thirdly, has to keep our game subjects marching perpetually along the horizon. So AI engines are also pivotal to give our characters the ability to create Skynet inside of our... No, just kidding. Usually an AI engine is more like a complex arrangement of behavior trees. But anyway, the point is that a game engine is the science-y programming skeleton that supports the game designers and lets them focus on the flesh, the story and gameplay elements of their title, instead of spending countless hours locked away in a room focused on, the sound, don't forget sound, and physics of, bouncing balls. Okay, so now that we have an idea of what game engines are for, the next obvious question is, where do they come from? Well, son, let me tell you, when a man loves a woman, and no, sorry, just kidding. So simply put, they come from, a lot of money. There are open source game engines out there, but for the most part, no one is building game engines just to help a brother out. And there are a couple of main reasons for a developer to build one. Number one, your company, let's say Epic, makers of Unreal Engine, or Valve, the makers of Source Engine, decides to focus on licensing this engine technology to smaller developers rather than trying to make every huge blockbuster game from scratch, or even the third episode of a blockbuster game. Number two, your company has the resources to absorb the multi-year investment into engine building to avoid paying out a percentage on future game sales. Blizzard would be a great example of this. Or number three, your company just can't find the right technology in a prepackaged engine and needs to build their own, whether they like it or not. So that's it in a nutshell. Achieving optimal cost efficiency and then, in some cases anyway, allocating those extra resources to other parts of production, like paying these guys to do voice acting, something I'm sure we all appreciate. And you know what else I appreciate? FreshBooks.
And at the sponsor point, we're done. Okay, so those are the videos. Hold on one second. Okay. So those are all the videos that I wanted to watch. However, there is one more link that I will leave you with. This YouTube channel called the Cerno. He has an entire series on game engines in C++ that you can actually follow along with. It's really in depth. He goes into everything in terms of OpenGL, everything you'll need to know. As you'll see here, it's like 92 videos in his game engine series alone. going through setting up your project, having window abstraction and GLFW. A plug here, we'll check this out. What is this?
This is the guy that I watched to learn how to do like OpenGL and everything. He had a really good tutorial, and he does all these different types of games with just like simple OpenGL graphics and everything.
Oh, I'm quite interested. Okay, so I will link all of those at the end. I should actually probably just link this in workshop text now. Might as well. That's that playlist. So back here, I have been working on a 3D engine this past summer using OpenGL and C++. So all the code for it's available on my GitHub if you want to go take a look. Here's the link. I can post that too, I think. If you do happen to click that link, please star the project. I need stars on my GitHub.
You're not allowed to plug for stars during workshops. I could have been plugging for stars all semester.
James, I'm just working smarter, not harder. Okay, so here is what I have so far. I'll just show you the main file. So I have camera locations stored in vector 3s. I could explain how delta time works. It's very important. So basically, if you are rendering a frame, let's say you're rendering it on two computers, right? And one of them is just much faster than another, right? And you don't have any sort of delta time calculations. Basically, the one with 1,000 frames per second will look much faster than the one with 30 frames per second.
Are you showing your code right now?
Oh, yes, I am. My bad. I have to change the presentation.
Yeah, I was gonna say we can only see the slides.
Yeah.
Thank you for reminding me. Screen 1. Now everyone can see?
Yeah. You should go get a video of what happens with Skyrim when you run it at 120 frames, just to show
I probably should, actually.
Not having good delta time can do to you.
Hold on, yeah, I can do that. Skyrim at 144 FPS. Glitch. Let me make sure this is the correct video. Yep, this is it. Okay, so this is basically what happens if you do not have delta time in your engine and you go. So the thing with Skyrim's engine is it's tied to, I believe it was 60 frames per second. So every single aspect of the engine is tied to 60 frames. So running it at 144 frames gives you this. You don't really need the audio for this, so I'll just leave it. But this is what would happen without delta time calculations, which I don't know how a AAA company did not implement that.
Ah, yes. The times 2. The times 2. Oh, that speed up. Oh, man.
As you can see, their physics engine has no idea what's going on because all the calculations are off because the math is not checking out. The horses are spinning.
Oh, that's funny.
Thank you, Todd Howard. Okay.
Thank you, Todd Howard. This is what happens when you try and set your frame rate to 60 and then people want to play at 144.
So basically, the way that delta time works is what you want to do is you use whatever language you're using. The OpenGL plugin that I'm using, GLFW, has one called getTime, where you can just call it and it will get whatever the current time is. So basically, you want to have two, variables. So you would say whatever the current time is, subtracted by whatever the last time was, and then what this will do is it will dynamically sync all of your animations and your physics calculations per frame. So you would, if you want to tie the movement down here in my movement script, where is it? Right here. So the movement speed is 2.5 times the delta time. So basically, if the delta time is higher, I will move faster, meaning so the less frames that I'm getting, the more time in between frames, meaning the less frames, I will be moving faster to sync up. as if I were... Basically, the speeds will be evened out depending on your frame rate. So it's very useful to have in your engine so you can keep moving. Next, so here's what me and James were talking about earlier about vertex buffer objects and vertex array objects. So basically, I have up here, I have one set of vertices. So these vertices make up a single cube, right? So one cube would require the 6 faces of it. So then I would store that into these objects down here. And then there's just a lot of OpenGL code here that I won't go into because it's very complicated and setting the vertex attribute pointer and stuff like that. But in this code right here, I just made a simple vector 3 array of size 512. So this is, I was kind of going for something like Minecraft chunk generation, if any of you have played Minecraft. I assume most of you have. So basically, if I run this, you'll see right here, I don't have, right now it's just a black background, but what I was going for is 3D chunk generation. So you can see that this gigantic cube is actually made up of just a bunch of tinier cubes. See if I go through them like this. So I have it generate multiple cubes, and probably the next step in this this engine would be to have a chunk object where I would be able to have multiple chunks generated at whatever size I would designate. So that would be pretty useful. And then so down here, I'll show one more thing in this. The main game loop here. So from here to here. No, wait. It's from here to here is what is constantly running nonstop until I press escape. So basically, it goes in, calculates delta time, processes the user's input with this function down here. Process input here. So it would get which key you're pressing, and then it would, like, say if you wanted to move forward, it would move the camera front forward by it would move the camera position forward by whichever direction you're facing, which would be the front vector, times the speed, which was times by the delta time, so it will be a consistent movement. And then after, where was I? Processing input. This is just OpenGL code for setting the background to be black, because you'd have to clear it every time. I believe if you don't clear the background every time in OpenGL, it will render over. I want to try that out, actually.
It's
maybe that would be
very funny. Do it.
Yeah, if I do something like this and then run it.
I'm actually not sure why that didn't work.
Yeah, me neither. Basically, it would just keep drawing over the same images. It would be like seeing after images.
Yeah, it's very funny.
Yeah. So then, I won't go into this too detailed, but you'd have a projection matrix and then a view matrix, and you would move all of the model's positions. You'd have to have a loop for every single model on the screen, and you'd move them based on the user's input. So basically, if you move to the left, you'd have to move everything in the scene to the right. So that is pretty much all the demo that I need to show. So does anybody have any questions?
You want to cover why we're using the matrices just a bit more? I don't think we should go like super in depth, but I do think that people should know about matrix transformations being like used in 3D graphics. Like
True.
I've done, I remember I did it a bit during the quantum mechanics workshop. I briefly touched on it. I sent an image in workshop text just representing how you
I feel like the best way to do it would be to just show it.
Space.
So let's show OpenGL matrix multiplication. I guess that would show transformations. Actually, this website right here, Learn OpenGL, is how I learned everything about it. So basically, there's really good pictures on here somewhere. So I will try.
Yeah, I know it's on here. It might not be on this one. I want the one where it's like all of the matrices lined up and they show you like the projection and everything.
I know what you're talking about. That might be under coordinate systems.
Oh yeah, right there. That's what I was talking
This
about.
one?
Yeah. How you basically you use your different matrices to basically just transform through until you can get the projection you want. And this seems
Yeah.
like really counterintuitive to anyone who doesn't know about this already, but like you can literally use matrices to transform your perspective in a 3D world based on like a camera position. And the thing that handles most of the math is the camera for matrix transformations.
Yeah.
Algebra.
So basically, in OpenGL, there's no native camera that can be moved around. So what you have to do is basically the camera will not move at all, but what you have to do is have variables of where you want the camera to be theoretically, which would be the position and where it's facing and such, and then move them. So you would change these variables, right? If you wanted to move forward, you would move this, like the X value, you'd make it 5 or whatever. And then what would happen is in the render loop, with the matrix multiplication, where is it? Right here. So when you would make a view matrix, you would have everything be translated -5. So if you're trying to move forward 5, everything has to get moved back 5. So if I hope that was a good explanation.
Yeah, it's really weird to think about because it's like nothing actually moves. The camera never moves itself. It's like everything else gets bent around where it thinks the camera is and where it thinks that the objects are. It's literally like instead of you walking around, it's like you have a pair of glasses that distorts reality to make it look like you're in a different part of the room when you press a button.
Yeah.
Like it's very interesting, and the math behind it is also very interesting. If you take a linear algebra class, I highly recommend right after taking linear algebra, take a look at OpenGL because it shows you like the real applications of matrices, and it's like more than the theoretical stuff. It's a very cool way to use linear algebra.
Yeah, transformations are fun.
Oh, they sure are. So I'm also going to link this website in workshop text because pretty much this is the only good resource that I've ever found for OpenGL. I mean, I'm sure there are YouTube videos like the ones that I linked and James linked, but for actually making progress and learning it, this site was like my homepage for like the past like 6 months.
Same. When I learned OpenGL, the site wasn't even as good, but it's gotten even better over the years. And even when I used it, it was the best resource online. But now it's by far the best resource for learning OpenGL.
Yes, I am a very big fan.
Of course, when you're doing an engine, the first thing you're starting with is the graphics because you want to be able to see stuff first, right? No point in doing.
Yeah, my engine literally does not have audio, physics, collision, anything yet, but the graphics are the most satisfying part of it. That's why I wanted to go for that first.
Yeah, and also, if you want to work on an OpenGL project, I wouldn't say me and Connor are professionals, but feel free to ask us any questions about the material that you see on like Learn OpenGL and everything, because I think we have a pretty good grasp of at least the big basic stuff as well. If anyone wants to do stuff in 3D,
I couldn't help you with advanced lighting, but I can help you with camera and the shaders and stuff.
Yeah. No, I always remember 3D was like the holy grail of computer programming. Once I learned how to like do games in 2D, I was like, "Oh, I'm just gonna upgrade to 3D. It's gonna be so easy." It is not, unless there are better ways to do 3D graphics, like less complicated ways that don't involve at the hardware level. In particular, 3JS and JavaScript.
Yeah.
Very comfy.
Also, one more. It's called like lightweight Java GL, something like this.
Lightweight Java game engine is.
This is what I believe Minecraft used because they used OpenGL, but in Java, not C++.
That's what I used for my engine, except it's literally just all raw OpenGL. I did not get any. It did not give me any help, unless it actually does offer help, and I just decided to use the low-level bindings exclusively. Like, that's entirely possible. But this is slow, by the way. I don't recommend lightweight Java game library.
If you're going to do OpenGL, I recommend just trying to learn C++ with it, because C++ is very fast.
Or C. Though I don't recommend doing a game engine in C because there's no objects.
Yeah. Well, anyways, back to the slides. I only have a few more, and then we're actually done. This is looking like it's going to be about an hour and like 5-10 minutes. So
good time scale.
So the next steps is, if you enjoyed graphics, you should look into learning OpenGL and shaders, and noting that OpenGL is quite difficult, but it's still much easier than DirectX or Vulkan. I have to say, though, OpenGL was probably the most difficult thing I've ever had to do in terms of programming, but once I figured out how to actually get it to work, I felt like a genius, even though it was pretty much just following learnopengl.org. It is very rewarding. If you enjoyed audio, you should look into the video that I linked. It's like an hour and a half, and it's very interesting. You should look into low-level audio libraries for C++, or whichever languages you like, but I prefer C++. And then audio file design. And if you enjoyed physics, you should look into taking more physics classes, and I mean that seriously. And because basically, if you think about it, there are a lot of jobs out there that, you know, they say like, oh, this isn't rocket science or anything, like it's not too difficult. But if you're making a game engine that involves rockets, your job is literally rocket science. So you should probably understand physics. And I recommend writing physics simulation using an established engine such as Unity for practice before you jump directly into making your own engine. But that's just my recommendation. So, summary, I hope you all learned more about the programming behind the game engine magic and walk away with a new interest. If you are very interested, on the next slide, I'll have a list of things you should study in order to get to the next level with these technologies. Whoops, those slides were out of order. This is what I meant by that. Okay, thank you everyone for watching, and stay tuned next semester for a potential follow-up workshop. And I will also stay behind afterwards if anyone has any questions or wants to learn more. So feel free to ask away.
Thank you, Connor. It was a great workshop.
Thank you, James.
Do we want to, you know what, never mind. I'll talk to you about that after it ends.
Okay. So does anybody have any questions?
I have a question.
Yes.
Have you tried other graphic APIs other than OpenGL?
Yeah, actually I have tried DirectX, and it made me want to tear my hair out. It's very difficult.
Why did you choose like OpenGL comparing to other APIs?
So first of all, OpenGL is cross-platform, so it'll run on, you know, Mac, Linux, Windows, anything. So it's probably the most universal out of them all. Also, there's, I would say, without buying textbooks or anything, there is the most documentation for OpenGL. So it's probably the easiest to learn if you're not trying to buy like 1,000-page textbooks yet.
Interesting. All right. Thank you.
No problem.
No, that's 100% right. I can confirm everything he just said. I tried Vulkan myself, and there's not that much good documentation on Vulkan. Vulkan kind of assumes that you already know OpenGL is the thing.
Oh, no.
Like, it's very, it's basically like they expect you to know, like, OpenGL 4 and, like, all of the features before you start using Vulkan, and it's very painful, and I was not able to get anything off the ground because there's just not enough, you know, starter code or examples to follow along with, and no good, like, real tutorials on it.
Yeah, if you are a learn by example kind of person, then OpenGL is directly up your alley. Anyone else have any other questions?
Yeah, I have one.
Yeah, sure.
So I think in one of those videos it said you can use JavaScript in Unity. So can you actually make a video game in JavaScript?
I know that Unity has JavaScript support. I've never used it personally because C# is just way better. But potentially, I believe you can write a game in JavaScript.
Yeah,
That's so weird.
I heard a lot of not a lot, but like I heard like people using JavaScript and Unity too.
Yeah, but the thing is, the way that the engine works, it would compile it down to, an executable anyway. So, yeah.
I mean, if the question is, can you use JavaScript to write a game, then yes. In fact,
3JS, right?
not even 3JS. Two of my best game engines that I've ever written are just done in like native JavaScript for the web, like pure and simple 2D graphics with the JavaScript Canvas API. And that's like two of my biggest game engines have been JavaScript. I mean, if you want to include the IEEE website, then 3 game engines have been JavaScript, but that uses 3JS. So yeah, you can write games in JavaScript, and in fact, JavaScript is I've personally found JavaScript very good to work in for game engines because you get the JavaScript isn't a slow language. This is a very common misconception that because it's interpreted, it's a very slow language, but it's actually, with Chrome's V8 engine, it's only about 3 times slower than C and C++, depending on the runtime conditions. So you can actually get some pretty good speed in browser and have like just good in-browser games. It's honestly mostly limited by the fact that it's so memory intensive. And the fact that the memory, depending on how memory intensive it is, that also can impact CPU performance and everything. So that's its biggest drawback. But it's not half bad. And I mean, with WebAssembly coming up, like we're gonna be able to get much better in-browser games within just like the next 5 years. At least that's my personal take on it.
Slightly unrelated, but like in less than 5 minutes, can you explain what WebAssembly is?
Oh boy. Do we really want me to? Maybe I should host a workshop on WebAssembly.
Oh my god.
WebAssembly. Okay, so I'll explain this very simply. So people probably know the difference between compiled and interpreted languages, right? A compiled language is compiled down into a like exe, or in Java a class file where it's like bytecode that's then recompiled. In between that, you have just-in-time compiled languages like JavaScript, where every time it's running an instruction, it's like basically going down and converting that into assembly instructions, and sometimes looking a few lines ahead before it's doing the conversion. And you can get surprising efficiency with this, like to the point where JavaScript is almost basically as fast as Java in some instances. And then you have languages like Python that are 100 times slower because they don't do just-in-time compilation, and they are literally interpreted line by line. So the interpreter is literally just like an if statement that's parsing every single line as you go down, which JavaScript used to be, but is no longer with the advent of JavaScript engines that do just-in-time compilation. So the real innovation with WebAssembly is the fact that you can compile your C code into assembly that can run on a web browser. What actually is going on is that web browsers have these stack machines on them that can run WebAssembly code that's guaranteed to be safe. Because you wouldn't want basically a web browser to give like programs access to like native hardware, but that the downside of that is you get the massive slowdown because you can only run JavaScript, which is sandboxed and safe. But essentially the innovation is that we are sandboxing faster code that's being compiled from C and C++ and other languages. Any language can be compiled into WebAssembly. It's language agnostic. So you can have, as long as someone's writing a compiler that compiles down to WebAssembly, you can get massive performance increases. It's pretty crazy. But I could honestly host an entire workshop on this because it's such an interesting topic, and WebAssembly is really going to be taking over in the next 10 years. I think we're really going to see a massive shift from JavaScript stuff, and even once WebAssembly becomes prominent enough, I honestly think we're going to see like AAA titles that you play in your web browser. Like it's not infeasible that as WebAssembly speeds up and everything just gets faster and faster, we're really just going to be able to use a web browser for like all of our gaming needs. I mean, you can already see that kind of happening, but like not to the point where we can run AAA titles. But honestly, I think soon that's going to be the reality. All right, enough from my rant.
If you're interested in WebAssembly, like you should look at the C# framework called Blazor. It is actually most popular web assembly framework that are used right now. If anyone knows that.
I should take a look at that. I've been staying away from the C# stuff. I've been mainly looking at the C and C++ end of things, but yeah, C# again, also a good option for WebAssembly programming, and it sounds like it's very popular now.
It was actually, the Blazor was a 2020 like most used, like most popular, like growing, like has the most growth in the like using like web API, not the API framework. Yeah.
That's very cool. Does it tie into like the whole .NET ecosystem, and like you can deploy it on your .NET applications? Is that why it's?
I'm not sure because I never used it. I just like looked at it when I was like doing learning C# and like .NET Core. It's very similar to like how you write .NET Core, but you can code like basically your website on C#. That's the like huge take for a lot of people.
Right, of course.
I don't like JavaScript. I don't like HTML, CSS. So for people like me, yeah, definitely it's a good one.
That's very interesting.
Yeah.
Thank you, Robin.
No problem.
Anyone else have any questions or comments or anything?
No, I was just listening.
All right, then. Then if no one has anything else to say, then I think workshop concluded.
Yeah, have a good night, guys.
Thank you. Everyone have a good night.
Thank you.
Good night, guys.
You as well. Good night, bro.
Good night.